Okay, good morning, everyone. Welcome to the second session of this seminar. Today, we will start with the presentation of Professor Patrick Wheeler from the Faculty of Engineering from the University of Nottingham in UK. Professor Wheeler received his bachelor degree from the University of Bristol and the PhD in electrical engineering for his work on matrix converter in the same university in 1994. And in 1993, he moved to the University of Nottingham and worked as a research assistant in the Department of Electrical and Electronics Engineering. In 1996, he became a lecturer in the power electronics machines and control group at the University of Nottingham, UK. Since January 2008, he has been a full professor in the same research group. He was the head of the Department of Electrical and Electronics Engineering at the University of Nottingham between 2015 and 2018. And now he is the head of the Power Electronics Machines and Control Research Group, Director of Global Engagement, no sé cómo se pronuncia eso, for the Faculty of Engineering, and he was the lead chair professor in Electrical and Aerospace Engineering. He's a member of the IEEE PALS outcome and also the IEEE PALS Vice President for Technical Operations. He has published more than 800 academic publications in leading international conferences and journals. Okay, Professor Wheeler, thank you very much for accepting our invitation. Here we have PhD students from the program of PhD program in engineering as part of the macro faculty project. So we are very excited to hear you and to see what we can talk about research in applied industry.
Okay, thank you very much for the introduction. I must send you a shorter version of that document sometime. And also a big thank you for inviting me here today. What I've been asked to talk about, I hope, is the way we work with industry. So what I'm planning to do is to talk a little bit, very little bit about my research group, and then look at some examples of the way we interact with industry and the different ways we do that, and more importantly, why we do that. It's very easy for the universities to say they have to interact with industry, but they don't always think about how to do it and the underlying reasons why we're doing that. I'm also going to talk a little bit about how we interact with Chile, because again, that's an example of my university working outside of the university in different ways. So I was going to include a couple of slides on that towards the end. So just to start with, I thought I'd explain where Nottingham was. So Nottingham is in the middle of England. We're about 180 kilometers north of London, sitting in the middle of the country. It's a small country, it's about 75 million people, but physically very small. If you take the outline of Great Britain as it's shown there, it fits into lots of bits of Chile in its entirety. The city of Nottingham itself has a population of about 300,000 people, and it's famous for a couple of people. If you followed soccer or football in the 1980s, you will have heard of our football team, Nottingham Forest, which was led by the manager Brian Clough. Sadly, the football team are not doing so well these days. They're in our second division. The other person sometimes people have heard of is the Tales of Robin Hood, maybe the Kevin Costner film of a few years ago. Robin Hood was stole money from the rich people and gave it to the poor. say he was a good socialist. And his enemy was the Sheriff of Nottingham, and we still have a sheriff today. We have a university of about 40,000 people in Nottingham, about 32,000 students. Within that university, we have various disciplines, including engineering. And within the Faculty of Engineering, I currently lead a research group, which is the Power Electronics, Machines and Control Research Group. So most of the examples I take in this talk are going to be around this research group. So one of the important things to note is that in a UK university, we tend to organise our research in large teams of academics, and we tend to work together quite closely. So for example, all our PhD students have at least 2 supervisors. Professors are good, professors know everything, but we don't know everything about everything. So being able to work with more than one professor means that you get, as a PhD student, you get a broader view of what's going on, and you can access more than one person's expertise, which works very well. So these are the professors in my research group. We work in electrical machines, we work in power electronic systems, we work in motor drives and the electrical systems they go within, and we work on the packaging and the integration of power electronic modules. We do this for a range of applications. So particularly at the moment, we're looking at transportation electrification or e-mobility. We're looking at that for aeroplanes, for cars, for trucks, and for boats, ships. We're also looking at how to connect renewable energy to the electricity grid. So there's a lot of work there on how to connect photovoltaics, PV, to the electricity grid, and also wind farms to the electricity grid. And we still do some work on industrial applications. So a lot of different things going on. We've also recently opened a brand new building. So I've got a 5,500 square metre building that was opened 1 year ago. So that's also quite an exciting time for us. When you look at who funds our research, so at the moment I have about 160 people in the research group. So that's about 20 members of faculty, 20 professors, about 60 postdoctoral research fellows, so people who have their PhD and continue doing research in the university, and about 80 PhD students, so people studying, like I believe many of you are. So about 160 people. And to fund all those people, we currently have about $45 million worth of research income. And that pie chart shows where that comes from. So some of it comes directly from industry, some of it comes with government support. So where it says TSB, TSB is a UK government agency. Some of it comes from the European Commission, and all of that is in collaboration with industrial partners. Some of it comes from the UK research councils, about 25% of our funding. That does not have the same funding with industry. That tends to be pure research funding. Some with overseas industry and some with what we call knowledge transfer partnerships. I'll explain those a little bit more later. So the important thing is there that we don't have one funder of our research. We have multiple funders, and 3/4 of that research, so 75% of that research, is linked with industry. So what this presentation is going to do is to explain some of the mechanisms for those links with industry and how they might work. I suppose one of the important things about the new building is we have a nice big new space. These photographs were taken just before we moved in. That motorbike is an electric motorbike. So of course it's allowed inside the building. Now that building is full of people and equipment. But that's giving us the home to about 180 people in the research group. It gives us some facilities to operate at large power and lots of space to be able to work. So that's quite important when we're working with industry, that we continue to improve our facilities and to show them that we have the space, the ideas, the test equipment to be able to work in a way that they understand and to test at the power levels that they understand. So it's quite important to be able to demonstrate the new technology. So the focus of that building is around those technology themes that I was just mentioning. And the funding from that building came from a variety of sources. It came from UK industry, came from UK government, and it came from the university. So no one person funded that building. Lots of people put the money into funding that. Just to give you an idea of how that building looks, we have a workshop up at the top right there, an area we can use for manufacturing the things we're going to work on. We have 3 laboratories: the high power laboratory, where we can work up to 20 megawatts, the main laboratory, there's benching there for about 100 people, and the power electronics laboratory, where we look at the smaller scale things that are happening. And finally, the office area, where we have desks for about 180 people. So a big space, a big facility, something that helps us to invest in industry. And this slide just goes through the types of facilities we have in there. So lots of different power supplies and lots of different equipment. And that's important because that allows us to be able to demonstrate to industry that we have the facilities to be able to do testing work. In a lot of cases, we have better facilities than our industrial partners. And that's important because that attracts them into our building to do testing work as well as research work. In terms of who we work with a lot of different companies. So this is just some of the companies we work with. The top half there are particularly aerospace companies. So you'll notice companies like Airbus and Boeing that make aeroplanes, but we also work with the companies that supply them. So the companies that supply parts of aircraft. So you can see there companies like Safran, Collins, Thales, Dassault. They're all companies that make components that go into the aircraft systems. So it's important to work not just with the main manufacturer that you can see, the Airbus or the Boeing of this world, but to also work with the companies that supply them. And you can see that again with the second set there, looking at grid connected power converters. So companies like GE and Siemens supply large power electronic converters that work in the grid, the type of converters that connect a PV, a solar generation area, to the electricity grid. But they rely on supply from companies like Infineon, Dynex, TT Electronics, Rome, to supply the components, to supply parts of those systems. So it's also important for us to work with those supply chains. And that's part of the success you have is if you work with industry, not working with just one partner, but working with a number of companies all working in the same area and often working as part of that supply chain. So working with the end seller of the complete system, the aeroplane or the power station or whatever it is, but also working with the companies that supply into that. Now, when we're working with industry, it's always a good idea to have a common language, a common way to talk about technology. And about 25 years ago, NASA in the US, so the US Space Agency, came up with the concept of technology readiness levels. These were then used across the aerospace industry and now across many industries, across many countries in the world. And this is a way of defining a technology. At what level is it? So technology readiness level 1 is a new idea. This is where your professor has had a good idea or what he thinks is a good idea on the way to work that morning. So he's got a really good new idea, totally untested, untried. It probably won't work, but it might be a really good idea. Okay, so that's technology readiness level 1. Technology readiness level 9 is when you have a product. So my telephone, my mobile phone will be at technology readiness level 9. It's not quite complete, you know. So my phone, made by Apple, they keep updating the software. So it's not reached total maturity yet, but it's a product that they can sell. It works, it does its job, it's well engineered. So we have to think about these levels when we're thinking of the technology and when we're thinking of how to get industry involved with those technologies. So as I say, technology readiness level 1 is a new idea, crazy idea, nobody's tried it. When we start getting up to technology levels 2 and 3, this is where that professor has given that crazy idea to a PhD student, and you've done some simulation, you've done some modeling, and maybe you've got something working on the bench in the laboratory. Okay, that's taking you up to proof that the research idea is feasible. And typically good PhD projects should operate in that area of technology readiness level 1 to technology readiness level 3. You're proving a new idea, you're proving some new theory, maybe validating that in the laboratory, and you're getting the idea that that research idea is feasible. Where does that need to go next? Where that needs to go next is through a whole process that takes quite a long time and money to actually prove that that is not just a good idea, but that it can work in a representative environment, that it can work in the way it's meant to. So you might have proved that you can do mobile communications by building the elements of a mobile phone on a bench in the lab and talking to another unit to the other side of the laboratory. To make it work in a representative environment, you then need to build a piece of equipment where you can go outside of the university and make that same concept work. So you're actually developing the hardware in a way that it will work in a representative environment, that it can be tested by other people, not by you. By the time we get to technology readiness level 6 and 7, we have a prototype that you can put in the hands of the general public, maybe in the case of a phone, and they can test it and they can try and break it. Okay, definitely something you wouldn't want to happen to your test rig in your laboratory. Okay, so that's really where that technology is beginning to mature. And then 8 and 9 is where you begin to do the marketing and begin to sell that product. So this is a slightly complicated graph where along the bottom I have the technology readiness levels, from technology readiness level 1, basic idea, through the basic research, typical PhD work, the applied research, the technology development, and into the prototyping and systems development. And on the vertical axis, there is the resource needed. And the red line on that graph is showing the amount of resource you need for that basic research, relatively high. And that's where you have academia, maybe government research labs, working on new ideas. To the right-hand side is where government and private industry invest. Government and private industry invest in these new ideas, particularly private industry, in taking these ideas from maybe technology readiness level 6 or 7 through into a product. And there's an area in between where in most countries there is not enough funding. An area where there's too much risk for private industry to take on the new ideas, but it's gone beyond the area of basic research that a lot of universities are set up to do. And this is where you might find science parks, innovation centres, government initiatives for technology transfer. This is the area where those great new ideas need to get into a product. And we call it the valley of death of good ideas, because if there's not enough funding in that technology readiness level 4, 5, and 6, then nobody will take the risk of taking those ideas through into industry. So one of the things we find is we need university, industry, and government funding to bridge that valley and to get those new ideas, which have been proven by you as PhD students in the laboratory, and get those into an industrial setting. Different countries deal with that in different ways. In the UK, we get funding from the government for universities to work with industry. And we have something called catapult centres, which again are meant to help in that area. In Germany, you get the Fraunhofer Institutes, which are funded to do that translation work, to go take the ideas from universities and put them into an industrial setting. So the different countries deal with that problem in different ways. So there's no one way that works for everyone. In the UK, they give people like me in universities some funding, a lot of funding, to do that type of work. So this is one of the things we're trying to do. And to do that, we end up with lots of different ways in which industry can engage with us. And this is just listing some of those ideas and some of those ways in which we work with industry. So there's not one solution to this. There's lots of different solutions, and they work for different research areas, different companies, and different individuals in different ways. So industry can fund big research centres within universities. So if a company really likes a whole body of work done by a team of people in a university, it might fund a research centre there to take those ideas and to be able to develop them, to take them through some of those higher technology readiness levels, actually within the university where that knowledge exists. Sometimes we get industry-led research projects where industry and government will fund us to do a project in collaboration. And that's one of my favorite things, working collaboratively with the engineers in industry so that the technology transfers between the university and the industry. And that can happen in the UK or over here in Europe. We often get that funded by the European Union. Sometimes industry will fund basic research, or sometimes the UK government funds basic research, and industry will be interested. They will be watching our technology to decide whether that's a good idea or a bad idea. Sometimes we get industrial research fellows. So industry will fund a researcher, but that researcher works in the university. That's really good because that person becomes a pipeline, a way of taking those ideas in the university and translating them into the industrial setting. Sometimes industry will fund consultancy. They will come to professors and offer to do consultancy work with us. That's very good for very short-term problems where maybe they need 1 or 2 days to get some direction. One of the things universities have to be careful of is that professors don't spend all their time doing consultancy work, because if we do that, we don't spend our time teaching, we don't spend that time working with our PhD students, and we don't spend that time doing research. So a little bit of consultancy is a good thing with professors. A lot of it is a bad thing. We have knowledge transfer programs. I'll talk more about those later. And there's technology licensing. Sometimes the university might protect its intellectual property. And I'm sure sometime during these courses, you're going to have a whole lecture on intellectual property and patents and protection of intellectual property. And sometimes we can work with industry to get them to license those patents and that know-how. And the university gets paid for that by the industry partner. And that can be another good way of transferring knowledge that has been protected. Often in engineering, patents actually can act as a barrier rather than an enabler, because sometimes it takes so long to get the patent in place, but by the time the patent's in place, the technology has moved on. So patents aren't always overly successful in engineering. they are sometimes very successful in science, and particularly in pharmaceuticals, medicines. So thinking about this pipeline, thinking about how we get these research ideas through. I said at the beginning that one of the things we often see is the idea of PhD students working on basic technology. Your professor's had a good idea. You start your PhD, your professor goes, I've got a good idea. I want to know if this works. And that's how they define your PhD program. And Professor Marco there, you know, his PhD project came out of a discussion between his professor and myself, where we had we had discussed an idea. We thought it might work, and it became Marco's job to make it work. These things happen, and they turn into big research areas. So those thoughts that come in to you as a PhD student, they can be really good, and they can really form new areas of research. But that's low technology readiness level. So at the bottom of this pipeline. When we start getting into technology readiness level 3, 4, that's where we start looking for government agency funded research projects. That's where we need a bit more resource to fund that work. You need more equipment to be able to build a validation platform and so on. Then we need industry to get involved. So when we start getting to technology readiness levels 4, 5, and 6, that technology development relies on industry, but it's too risky for industry to do on its own. So you need some government resource there, or some venture capital resource there, if it's going to be very profitable, to be able to fund that technology development and to remove some of the risk from industry, so that they can take on those new ideas and build up that knowledge and those technologies. And then once you start getting to technology readiness levels 6, 7, and 8, that's where industry itself has to invest. It's got a prototype, it then needs to take that on to a product, and that's where industry itself has to borrow money or use capital it has to invest in that technology to get to that new product. So do PhD students have an important role in this pipeline? Well, yes, that basic research relies almost extensively on PhD student projects. And that's the important part. Sometimes those PhD students follow that pipeline, that they then become a postdoctoral research fellow, and then they go and work in industry. So they might follow that technology all the way up through that pipeline. Sometimes PhD students become professors, and their job becomes to have the new ideas that feed in the new ideas into that pipeline. Okay, so different people take different positions in that, but it's an important pipeline to remember. Ideas don't jump from technology readiness level 2, where you've got something basically working on a bench, to being a product overnight. It takes a lot of time and a lot of resource to go up those technology readiness levels. So I've got a series of case studies, and I'll pick up on a few of these and just expand on them. I thought I'd start with something large and something European. So the European Commission is very good at funding very large projects. This one was worth 1.6 billion euros. That's about 1.8 billion US dollars. That's a lot of money. Why did the European Union decide to invest so much money? Well, this is aerospace. This is about making aeroplanes less environmentally damaging. So how do we make the airplane more efficient? And eventually, how do we make the airplane so it has zero impact on the environment? So if we go back to 2008, they started investing 1.6 billion euros, and they were going towards the Akari Goals. So the Akari Goals was an aerospace industry set of goals looking at reducing fuel consumption, reducing emissions, and reducing noise from aircraft. We always forget about noise, but if you live near an airport, you don't forget about it. it's another emission from aircraft we have to remember. Within this project, my team at the University of Nottingham had about $11 million to spend on research. And this is where we were taking ideas that we'd already done PhD projects on, and we were putting those into demonstrators, things that would actually go in the future onto aircraft. There's 3 examples of the work we did there. So the first example was in actuation, looking at building an electromechanical actuator for use in a large helicopter. So this is how you control the helicopter. This was traditionally done with a hydraulic system, and we looked at solving the problems to do that, both electrical and mechanical, with an electrical system. So very demanding application, an application that was flight critical, and something that was good fun to do. The next project we looked at was in reducing the fuel burn from aircraft when they're on the ground, when they're moving around the airport. So we designed a motor that goes inside the wheel of an aeroplane, so that when the aeroplane is going from the terminal building to the runway, it does it using an electric motor, not using the big inefficient gas turbines. By doing that, you can save a lot of fuel. But it's a very demanding application for a motor, because to start a stationary aircraft on a slope at an airport takes a lot of torque. And you're in a very hot place down near to the brakes of the aircraft. And the third example there is looking at a generator. When you're on an aeroplane, you have lighting, you have avionics. We're trying to make a lot more of the systems electrical. So we looked at how you design a generator to make it as small and light as possible. So when you're working in aerospace, you don't work around cost. If it costs more, but it weighs less, then that is good in the aerospace industry. So you spend a lot of time making things smaller and lighter, so you can put more passengers on the aircraft. You don't spend your time making it cheaper, because the expense will come back later in the lifetime, because you use less fuel on the aircraft. So there's 3 examples of 3 demonstration projects we did as part of that first program. As I say, there's a long timeline to this. So that first program lasted 7 years. We're now in Clean Sky 2, where Nottingham has a budget of around $60 million, around 54 million euros. And every one of those words in those white boxes is a demonstration project we're doing as part of that program. So all that work we did in the first 7 years, we've now got another 8 years of funding to continue to take those technologies up those technology readiness level scales. And most of these projects are working up to technology readiness level 6. So the stage before we put them on an aircraft and actually go flying with those systems. So a big long lead time and a lot of work that goes into developing those, and a lot of money. 54 million euros sounds like a lot, but the whole of that program that we're working in is 4 billion euros. The follow-on project from this, Clean Sky 3, looks like having a budget of around 5 billion euros. So this will continue for another 7 years. So at the end of this, we would have been working on these technologies for 22 years. Okay. By the end of that time, we expect some of the early technologies to be flying on aircraft. Okay. So from the PhD projects to flying on an airplane could be about 20 years of technology development. The aerospace industry is quite slow in adopting these new ideas because of concerns about safety and so on, but it just shows how long it can take and how much money it can take to take an idea from a good PhD project into something that's actually going to have an impact, in this case, on the environment. So another thing we've been looking at is how we fly electric aeroplanes. So going all the way of getting rid of fossil fuel and actually flying an aircraft electrically. And the reason I've included this is this shows that we don't just get funded from one source. So you'll see 3 demonstration aircraft there that are all going to fly in the next 5 years. So those aircraft platforms, 2 of them already exist. The Challenge to Zero project, Future Flight project will exist soon. So there's 3 different platforms. We have projects developing the propulsion motors, so replacing the gas turbine on the wing with an electric fan on all those different aeroplanes. So the top aircraft there is a 90 or 100-seater regional aeroplane, the type of aircraft you might need to fly between cities in Chile, with a relatively small capacity. And we've got 3 projects there which are all looking at the technologies we need for that. So that's all European funded. The middle aircraft is an airship. So that is a big balloon filled with helium. So it's the same weight as the air. So the aircraft needs no energy to make it float, to make it fly. You only need to put in the energy to make it move forwards. So that's why it's big and bulbous. It's because it's full of helium and it's basically an airship. But you need you need motors to make that fly. At the moment, they use diesel engines, but hopefully in 3 or 4 years' time, we will be flying that with full electric propulsion using batteries. The reason for that is it flies quite slowly. We don't need to use energy to keep it flying in the air. So the energy you need to put in is only to make it move. And for that reason, we can do that as battery-only flight. So that's funded by the UK government. And then the UK Flight Challenge is a project funded by UK industry, a little bit of UK government, which is developing a very small 2-seater aircraft, which is all electric, but it's a platform for future technologies to try things out and to go flying with them. So a really good demonstration of industry getting together so that it can look at the systems in that technology readiness level 6, 7, and 8, and actually put them on an airplane and fly them. So a good way of accelerating some of those ideas. Now, so various different funding mechanisms there. Another one we use a lot in the UK is the Technology Strategy Board, sometimes referred to as Innovate, which is funded by the UK government. So this is the UK government giving money to industry, but to get that money, industry has to work with universities. So the government does not give the money to the university, it gives the money to the industry partner. The industry partner leads the project, but the project does not exist unless there's a university working with that industry partner. So we get our money because the industry has applied for it and got that money from the government. So this is just an example of that. This particular example is again aerospace. It was led by Airbus in the UK. So I think that's come out badly on your screen, but hopefully you'll be able to read that. And this was looking at the actuation of landing gear on an aeroplane. So looking at what happens if we make that all electric. This is a technology that we know because we've done some PhD projects on it. It was a technology that Airbus wanted to know about because they think they can save weight on the aircraft by having an electric actuation system. So we built some hardware and then we went and tested it at Airbus on a landing gear of a test aircraft. So this was taking things we knew, putting them on an airplane and actually testing that and seeing if it would work. Only in a hangar, we weren't flying with it, but it was on a full-sized aircraft. So a good example of how the government enables us to work on a project with industry by funding industry to work with the university. when we begin to look at motor drives, we have a lot of examples of technology transfer projects. So these are just some of the ones we've done with industry. So the one in the top left is a power electronic converter that is integrated with an electrical machine. So that's the end plate of the electrical machine, but with the power electronics built into it. And with that project, we're working with a company in the US who launched a product earlier this year. So that was a project that was a research project at Nottingham when I first came here about 26 years ago. It was my first government funded research project. 25 years later, we've got to product. So it just shows you how long those things take. The picture in the bottom right is a 450 kilowatt project we built with industry, which we thought would go onto a ship. So for a ship going out at sea in about 5 years. It's taken a little bit longer. We've just started the project that will transfer that into a product. So that's probably another 5 or 6 years from a project we started about 10 years ago. But another example of something that's going through. Those of you who know Professor Marco's research work will know he has an interest in matrix converters. So I thought I'd focus a little bit on that one. So this is that integrated motor drive where we took a standard motor, we integrated the power electronics of a matrix converter, power converter into that motor, and it's all housed in the end plate. But the final product looks exactly the same as the original motor. So we've integrated all that power electronics in there. How have we done that? Well, we've done that because we understand the power electronics. We've also done that because we understand the thermal management, getting the heat transfer from that power electronics into the air. So what you can't see in that picture is a total redesign of the heat sink to get the heat out into the air and the fan. So that's also very typical in engineering, that the further up the technology readiness level you go, the more different types of engineer you need to involve in the project. So in that project, it wasn't just about electrical engineering, it wasn't just about power electronics. We had to deal with the mechanical integration and we had to deal with the thermal management. So we had to be an expert at electrical machines, at power electronics, at thermal management, and in mechanical integration. So at least 4 or 5 PhD students for the basic technology, followed by a large number of years of research fellows and engineering time to put those products together. So these things always take time. Another way we can work with industry, when we work with industrial partners on the technology transfer projects, we always find they have good ideas. Professors are good at good ideas and new ideas and novel thinking, but our industrial partners are also good at that. And so sometimes it's a good idea to work on PhD projects with an industrial partner because they've got some good ideas. They know the problems they might need to solve in 5 or 10 years' time for their business. So one of the ways we do that in the UK is through something we call a doctoral training centre. And my research group has one of those in collaboration with the University of Newcastle in the northeast of England, in the area of systems for electric propulsion. So I thought it was worth having a look at this and how this works. So EPSRC is our UK government funding agency, and they give us money for this centre for doctoral training. And how this works is we have 2 universities, Newcastle University and the University of Nottingham. And at the moment, we have 31 industrial partners who are involved in that project. And we're expecting to train 50 PhD students over a 5-year period. And we're about halfway through this at the moment. So the vision of this is the creation of a new generation of UK specialists in driving the electric revolution in the transport sector. So notice that this is not about new ideas. The vision is about the fact that the PhD is training people to be able to realize transportation electrification in the future. Because the funding for this came from the idea that if we don't have people doing PhDs, then industry in the future won't have good people who can work on those technologies. One of the things we're trying to do through this is to obviously have the research on the right-hand side of that diagram, as you would expect from a PhD program, to having some taught modules and some learning. Well, as PhD students, you're obviously doing that today. But also to have some professional skills that are also developed through this program, and to do that through collaboration with the industrial partners. So it's an integrated PhD program where the university is doing some teaching of some theoretical work. Fine, we're happy with that. But also industry is working with the students to develop their understanding of how industry works and how the research goes through those technology levels until you get to a product. So important way of doing that. And because it's a big center, then all these students work under taught together, same way that you're finding yourselves. So in the first year, we spend a lot of work training the students, doing the thesis research and the cohort-based activities with our industrial partners. And then in the following 3 years, there's a lot of work on the research, but also the students go out and spend 3 months every year working with their industrial partner. What these slides don't say is that that industrial partner is putting in half the money for this program. So it's funded 50% from the UK government and 50% by industry. If industry doesn't give us half the money, the UK government will not give us the other half. Okay, so all the UK government is doing is doubling, multiplying by 2, the UK government, the industry money, so that we have the money to work on the scheme. So there's a lot of incentive there for us to get industry involved and to get them paying. Industry like it because for every pound they pay into the scheme, the UK government pays £1 into the scheme, and they get to work with the PhD students and to try out some of the new ideas and to try and solve some of the problems that they have. All the PhD students also have 2 supervisors in the universities. So they get the academic side from the university professors as well. So those are the sorts of things we're trying to do there. The way we get these funded is being very focused. So this CDT focuses on electric propulsion across transportation sectors. So we're only doing transportation electrification. So this project is going to fund 50 PhD students, which is a lot, but only in that transportation electrification sector. And to give you some idea of the companies who are funding that, those are most of the financial supporters of that program. So some of those companies you may have heard of. Dyson are there. I think Williams, who race cars. So Williams do race in Formula 1, but they also race in Formula E. So they build race cars. Control Techniques, for example, make motor drives, hundreds of thousands a year, and so on. So a lot of companies you'll have heard of, and a lot of companies you won't have heard of. If you drive a German car, AVL will have made some of the electronics in that car. So companies you won't necessarily have heard of, but whose products you use potentially every day. So a lot of different companies involved, a lot of companies spending their money on those students, and on the development of that technology. So the final link I wanted to talk about was just a link with Chile. Why is this important? It's not really about, well, it's not about industry links, but it is about developing research and making research interesting. And I thought, because you're all at the Universidad de Talca, or universities in the group, that it would be worth just mentioning this. So I'll have to apologize because these slides are a couple of years old. Some of the data is slightly out of date. But we did some mapping a few years ago of where my research group worked in the world. And you can see that we work with a lot of European countries, and we work with university in the States, some in Australia and China and so on, and with a load of universities in Chile. So my research group is very strongly linked with Chile. And over the years, this started back in the 1980s, over the years, you can see the number of papers and number of citations that we publish has increased as we've been working and collaborating together. So collaborations aren't just with industry. Researchers can collaborate with researchers in different countries. It's a great thing to do because we have a different way of working, different way of thinking, and we have different ideas because we have different backgrounds. So it's been very successful. And you can see that we've won a lot of prizes for collaborative papers in research and so on. These things don't happen because we just want them to happen. They happen also because the people with money, the funders, want them to happen. And when we look at who's funded that over the years, we've had funding from the UK, from the British Council, from the British Embassy in Santiago recently as well, through various schemes. We've had funding from the European Union. So the European Union will fund entities in Chile and entities in the UK to work together. We've had funding from the Chilean side as well. It's now ANID, but through Corfu, Fonasit and so on. So there's different ways there in which we can fund these programs. And all of those funding sources are enabling us to collaborate. And the reason they do that is just in the same way that working with industry adds value, working with strong partners overseas works very well, and adds a lot of value to the money that's spent on the research and the ideas that we get from that and the experience that we get from that. So a lot of different ways of working and a lot of ways in which we can collaborate. So trying to bring that together. So Nottingham has one of the largest research groups in our area in the world, and our research spans that basic technology levels 1, 2, and 3, right through to the applied research where we're building demonstrators with industry. And we're very lucky in that we get funding at all those different technology readiness levels. And I've given you some examples of that as we've gone through that. As a research group, we're always committed to working with industrial partners. And there's reasons for doing that. One, they give us money to carry on doing our research. That's always good. But more importantly, it means that our research remains relevant and it gives a way in which our research can be exploited. And it's important that we don't do research for the sake of doing research. That research has to be good and has to have relevance to mankind. Otherwise, why is it being funded? What's the purpose of doing that research if that understanding doesn't give benefits to mankind in time? A lot of the research we do, we feel has a lot of benefit to society because a lot of it is around transportation, electrification, and connecting renewable energy to the grid. And those are both things we need for the sustainability agenda. They're both things that were talked about a lot at COP26, which was held in Glasgow in Scotland last year. And there has to be a sustained long-term element to that. And the other thing is, it's very easy to think, I've done a really good PhD, everybody must like this idea, and I must be able to make money from it. The answer is yes, a lot of PhDs will make money. A lot of those ideas will eventually get into industry, but it might take 25 years before it does, and that's exactly where a lot of basic research should be. We should be solving the problems that industry doesn't want to solve yet, because it doesn't need that technology for another 10 years. But our job as researchers is to make sure that we're feeding that pipeline with good ideas, so that when industry does need those solutions, it will get those solutions. And by working with them, we can begin to understand the problems they don't realize that they yet need to solve. We can solve them before they actually come to us and ask. So thank you for listening. Marco, I hope I've said some of the things that you wanted me to say, and I'm more than happy to answer any questions that people may have.
Okay, thank you very much, Pat, for your very kind and interesting presentation. I think that it provides us a very good view of the situation and the level that universities in Europe work with industry. Now we have some time for questions and comments and the participation of the students. So I open the microphones for the students. So if they want to say something or to ask you something, now is the time. ¿Alguien que quiera hacer alguna pregunta, algún comentario, alguna inquietud? Lo puedo hacer. Lo puedo hacer en español también y lo traducimos. Roberto.
Yo tengo toda la presentación interesante. Lo podría hacer en inglés, pero no practico hace como 10 años, así que lo voy a hacer en español. Pero tiene que ver cómo evitar el valle de la muerte, que es la relación entre la investigación dura en una universidad y la aplicación industrial, porque los fondos a veces no son fáciles de encontrar. Eso me pareció interesante, que hay que dar luces o caminos para poder evitar ese valle de la muerte. La mayoría de los proyectos caen ahí.
Ya. Pat, Roberto said that it's a very interesting presentation, and his question is how to avoid the valley of the debt. As you mentioned, for that, you need to invest. Is the only solution, or there is something else?
There are lots of solutions. So the first thing is to identify the fact that sometimes in a lot of technology areas, there is this gap between the really good ideas and the basic research and products. It doesn't exist in every technology area. Mobile phones is a good example. So these things is a good example of where that gap does not exist, because these companies invest a lot of money in research. But in some areas, there is a big gap. How can you bridge that gap? Well, you either need government intervention, so you need money from governments to encourage and to enable universities to work with industry. So the example I gave of the actuator, the UK government gave a lot of money to Airbus, as long as Airbus worked with the University of Nottingham to demonstrate that technology. So that's a way a government can get involved. The other people who get involved in that space are what we call venture capitalists. So these are people investing lots of money, millions and millions of dollars, in new companies that take good ideas and take them on into a product or towards a product. Now, we're seeing a lot of those companies in the aerospace sector. So for electric flight, we're seeing a lot of new companies saying, we're going to make an electric aeroplane. And the reason those companies are doing it is because they recognize that there's a lot of potential, that people want to fly an electric aeroplane because it's better for the environment. And people, the investors, the people with hundreds of millions of dollars to invest in new companies are investing in it because they see that market opportunity and they see the technology that's been developed in the universities. So they'll create a new company to develop that technology. Now, that company might not actually ever build an aircraft. What might happen is when that technology has been developed and it looks very good, then Boeing or Airbus might buy that company so that it can then use that technology in all of its airplanes. And then the investors get their money back by selling that technology company. So a good example there that you might know is Tesla. So Tesla took lots of venture capital money in the US and started developed the technology and started selling electric cars. He hasn't sold the company. The company is now worth a lot of money, far more than the investors put in. So he can pay the investors back and continue to build that company. But that was a company that was built on investment money from venture capitalists. So 2 stages. One is to find lots of money that puts industry together with universities and good ideas to develop that new technology. And the other one is to, first of all, to actually identify the industries where there is that gap. And the electric car one with Tesla is a good example because Ford and General Motors and Nissan were not investing money in electric cars. So those good ideas were stopping. And Tesla was the company that was formed to take those good ideas and to put them into profit and to help with the environment. Sorry, that was a very long answer, Marco. But
it was okay. Thank you very much. But, ¿alguna otra pregunta? Any other question, comments, opinions?
Yo tengo una pregunta.
Jorge.
Perdón, Alejandro. Gracias. Oye, lo que pasa es que quedo con la idea de que hay mucha investigación, pero en este caso el hilo conductor es la parte eléctrica electrónica. Pero sabes que yo tengo una pregunta más global, porque en realidad se habló de proyectos muy relevantes de alto impacto, pero ¿qué opina él o cuál sería el hilo conductor para proyectos tan potentes? Necesitamos un equipo multidisciplinario. ¿Y cómo se consolidan esos equipos con tanto conocimiento similar? ¿Cuál es el hilo conductor para llegar a puerto y tener un resultado potente? Ahí está hablando de la posibilidad de motores eléctricos en la aviación. Entonces, ¿cuáles podrían ser las claves? ¿Qué opina el especialista este? Por favor.
Okay. Pat, Jorge has the question that how to make it work in terms of, okay, there are a lot of good ideas and there is a lot of people, and how to integrate everyone to do and to work in a very huge project. There is something key, and which are the keys in order to make it happen?
Whoa, that's a big question. So when we work on the big European aerospace projects, which are, the current project is 4 billion euros, we have an office of maybe 12 people in Brussels that coordinate that. And they control it because they control the money. And the only way you can control big projects is by controlling the flow of money, because it's a very powerful tool. So you have to have good project planning, you have to have professional project planning, and you have to have tight financial controls to get people working so that everybody is working in a coordinated way. So with the big, well-funded projects, that is a really good technique. You use the finance, and you don't pay people for their research work unless they've delivered the research they said they were going to deliver. And you do that through good project management. If you're at a lower technology readiness level, and you can do it around a challenge. So it's only 50 people, but our Centre for Doctoral Training that works because we've got the challenge of developing the technologies around electric propulsion. And we've got the need to bring in industry. So as academics, that project is always going to work because we're very motivated towards electric transportation. We have lots of ideas. And to get the government funding, we need to go and find our industrial partners and ask them for just a little bit of money. And so it's that money that again makes it work. But as a professor, I'm highly motivated to do it because there's this big challenge of electric propulsion. Now, the advantage that gives us is that the students who are working on that project, the PhD students, are all working around a common theme. And we do lots of things with them, lots of training with them to make them work as a team as well. So as well as their individual PhD, we're encouraging them to work together and do some teamwork. And that works very, very well because people often work better in a team when they can compare their experiences. So getting that communication is another vital part of that. So yeah, the big finance projects with industry use money, but getting people working closely together and enjoying working together and benefiting from that in their PhD projects, for example, is another way of doing that. So I hope that answers the question.
Okay, thank you, Pat. Jorge, no sé si responde a tu pregunta o quieres comentar algo más.
No, si se ve bonito, oye, me quedo con las mismas dudas, pero está bien, está correcto, muchas gracias.
Alejandro.
Sí, hola. I will try to practice my English, but first of all, thank you for your presentation. Very, very interesting. I have two questions for you. One of the first is, what role or space is there for small businesses and local businesses in this scheme? And the second one is about social validation of the research. Do you have any system of social validation within the university? I mean, perhaps Airbus does motors for civil planes, but also for military purpose. So do you have any system for that, for acknowledging that?
Your microphone is off, Pat.
Oh, sorry. So I'll take the second question first. So when that is it's a very topical question, and when you have technologies that are dual use, so they can have a defense, military use, and a civilian use, then there's a big ethical question. All I would say is that if you use a mobile phone, it has 12 switch mode power supplies in it. Switch mode power supplies were first designed for use in military applications, military satellites. So if you have a mobile phone in your hand, you're using a device which has been enabled by military funding. That adds a big ethical question to everything we do, because a lot of technologies have dual use. Switch mode power supplies went from a military satellite use to every piece of electronics that you would ever use. So is military funding for research wrong or right? That's an ethical question that we all have to think about. My personal view on it, and it's my personal view, not my university's view, is if I see a technology that I'm working on which is good for the environment, that's going to save energy in an industrial environment, is going to enable electric transportation and help the sustainability of the planet, I think that's good. If there's a second use for that might be helping fly military aeroplanes, so be it. And if the military want to fund that because it's good for defense, but I can see the route to a civilian use that's good for the environment, then will I take that money? Well, the answer is probably I will, because I can see the civilian use for it. But it's a difficult question, and everybody has their own ethics around that. At the level of a university, that becomes a very, very hard question. And we actually at Nottingham now, we actually have a unit called Trusted Research, which tries to provide unbiased information to professors so that we can make our judgments about that. So they will look at research funders, they will look at the history of that research funder, and they will look at where the ethical questions might be. So they will give an unbiased set of information to us. The decision remains with me as a professor, not with the university. But as long as it's not going to destroy, there are some people they won't fund because it would damage the university's reputation. So there's some countries I can't do military work with because it would be bad for the university's reputation. And they will say no. Most of the time, that ethical question is mine to answer as a professor. And I have to go with my own ethics on that. And that is difficult. I accept that. And that's the way it works. So a very, very good question and a very difficult question to answer. And yeah, anybody who says that they don't want anything to do with military funding, the first thing you need to do, I'm afraid, is throw your phone away. Because it relies on switch mode power supplies funded by the military. The second question is a really good question too. I work with a lot of small companies on technology transfer projects. Small companies are very good at taking good ideas and getting them to market quickly. They're better at it than big companies because they haven't got so much money invested in a particular technology and a particular way of doing something. So actually, when we work with a small company, so Tesla, the example I was giving earlier, started off as a small technology company. Okay, it now produces hundreds of thousands of cars every year, but it started off taking the electric transportation technology and developing it very quickly because it didn't have an existing platform. It didn't have whole factories making petrol, gasoline engines. So it didn't have that history. So sometimes it's a good idea to work with small companies because they can develop more quickly. And they're often more receptive of new ideas. But they do need support for doing that. So local government, national government really does need to invest to enable them to do it. And the other thing we find is that when they do get that investment and when they do work with universities, they benefit a lot, not just from that one technology, but actually from the conversations that you have over dinner, over coffee, where they might have a small problem and we have a solution to it. So I always find when I work with a small company, I might do a little bit of consultancy with them. They might be sponsoring one of my PhD projects on the Centre for Doctoral Training. But the real value to the company is in those conversations because they find solutions to problems. We find new problems that they need to solve. And it's in that exchange that they get value. So the hardest thing for a small company is to make time. It's not normally the money, it's to make time to have those conversations and to get that interaction. But when they do, they benefit.
Thank you, Pat. One more question. Alejandro, ¿ibas a decir algo? ¿Ibas a decir algo?
No, solo gracias. Thanks.
Okay. Okay. ¿Alguien más tiene alguna pregunta, algún comentario?
Me. Yes, good morning, Pat. Very interesting presentation. I have a question. Does exist carbon funds or sustainable fund finance applied research? Because you are discovering a new trends in engine and motor with electrical solutions, but there are another industries investing in this solution mixed.
We're finding a lot of industry, right? So our government funding is focused on the government priorities. So certainly for the last 2 years and probably for the next 10 years, there is a big government priority around sustainability and the move away from gasoline or petrol, diesel vehicles to electric transportation. And that's all around COP26 and the whole of that sustainability agenda. So what we find is that a lot of the UK government money is focused on that agenda. It might come through different agencies, it might be for research, it might be for technology transfer, it might be for industry. But to get that money doesn't just go to any company, it goes to the companies that have ideas and the universities that have ideas that match those priorities. So I would almost argue that a lot of, at the moment, it's a good time to be in transportation electrification and electrical engineering and the technologies associated with that, because in a lot of countries around the world, that sustainability agenda is a big agenda. So it's not really a fund for doing that. It's that the funds that the government have, that's one of the main priorities. And that's certainly how I see that at the moment. We have another priority in the UK around healthcare and immunisations and future pandemics at the moment as well. So the government has a number of priorities, and it's the research in those areas that benefits from that. And I think everybody in this room in engineering at the moment is benefiting from that sustainability agenda. Not sure if that answers the question quite, but we need our politicians to make that agenda correct.
Great. Thank you very much, Pat, for your time. Vamos a dejar hasta aquí las preguntas. Now we will leave you.
Muchas gracias. Thank you all for attending, and I hope you found some of that useful. And Marco, thank you very much for the invitation.
Yeah, thank you. Thank you for our invitation, and keep in touch. Bien, el profesor Wheeler tenía que retirarse ya. Y también doy libertad de acción a las personas que llegaron como invitadas aquí al curso. No es que te esté echando, Andrés, solo te estoy diciendo que tienes libertad de acción si te quieres retirar.
Algo no sé he aprendido a tener práctica. Me estaba escribiendo en el chat que me voy, así que nos vemos. Chao.
Bien. Bueno, muchachos, voy a llevar la grabación.